joint work with Matthew Kanch and Sébastien Gom, both of which are here today. So most of us walk around today carrying a Wi-Fi enabled. Sorry.
Use the mic.
Is hello? Okay. Sorry. So most of us walk around today carrying a Wi-Fi enabled device in our pockets, whether it's a smartphone, a tablet, smartwatch. And these devices, everywhere we go, they keep on broadcasting a unique identifier, the MAC address of that device. This is the case whether the device is actually connected to a network or not. Because this MAC address is tied to a device, and that device is carried by one person, this kind of information could be captured to measure and analyze human activity. For instance, it could be used to find the number of visitors to a particular location, how often do they go there, and when they go, how long do they stay, and if they want to move from one place to another, which path they are most likely to take. There are a few systems deployed to compute this kind of information. However, the industry standards for this kind of data collection is not good enough. For instance, most companies use simple hashes to protect the MAC addresses from being re-identified. However, it has been shown that these kind of hashes can be reversed just in a few minutes. One of the reasons is that the space of all MAC addresses is just not large enough. What we want to protect is not just the result of the analytics, that is the number of users in the place, but also the internal state of the system to allow us to, so that we don't have to trust the data curator, the person or the entity collecting the data, and also to protect it against potential intrusions or breaches. So in order to do that, the data must be sanitized on the fly as soon as the MAC address is observed. The kind of the definition we try to satisfy is called pan-privacy. It has been introduced in 2010. It's, informally speaking, it's just a property of an algorithm saying that it's both its internal state and output do not change much if one more MAC address was added or removed from a data set. The intention behind this kind of definition is that if the adversary has access to this data, it won't be able to distinguish whether a particular MAC address was in the data set or not. In our approach, we depend on an observation that has been made before, which is that physical mobility analytics could be based upon some primitives, in particular cardinality set operations, like the intersection, the union, and so on. For instance, the number of visitors in a place could be just the cardinality of the set containing the unique the identifiers of the people that has been observed in that place. And so the amount of time they spend is just the intersection of the few sets that has been collected over time. So the key idea behind that approach is to design a privacy-preserving data structure that allows us to compute this kind of cardinality set operations while preserving the privacy of the user. This approach is actually agnostic to the data source. It's not limited to Wi-Fi. It can be applied to any system with unique identifiers, including cellular data, like call detailed records, which are collected by cellular operators, or even web analytics, in which the identifier, in this case, it could be the IP address. The data structure we design is based on Bloom filters, which we will describe in the next slide, that are perturbed to ensure differential privacy and the pan-privacy property we described before. It's non-interactive. It means that we can collect the data even before we decide what kind of mobility analytic we want to compute. It's decentralized so that the sensor nodes collecting the data do not need a central aggregator or coordinator between them. So a Bloom filter is basically a data structure used to represent sets. It's a bit vector has two operations, insert and contains. An instance of this data structure is associated with a few hash functions, and for a given element, we pass this element to the hash functions, which point us to a particular bits in the bit vector. To insert the element into the Bloom filter, we set all these bits to 1. To query if an element is in this data structure, we check if all these bits are set to 1. Of course, there is a small probability of false positives because of the hashing collisions, but it gets much smaller when the data structure size is increased. Bloom filters has been extended in 2012 to ensure differential privacy simply by flipping each bit identically and independently at random with a probability less than half. 2 years later, there was a first estimator for the cardinality of the set represented in a blip has been proposed, and 1 year later, an estimator for the intersection of two sets has also been proposed. In our work, we extend blip to support band privacy so that it can be built on the fly. Instead of initializing the Bloom filter with all zeros, we initialize it randomly from one distribution, and when we insert an element, we don't set the bits to 1, we set them randomly, but from another distribution. So it's simple to implement, it doesn't incur additional cost except for generating of randomness. And to count the elements of the sets, the intersection, the union, and even higher cardinalities, it suffices to treat the bit vectors as vectors over the integers and add them together. That is speaking for unflipped Bloom filters, to simplify. In case, here this is a Bloom filter which has zeros and has ones, and this is another one, and we add them together, we have a new vector which has zeros, ones, and twos. Then we tally these to get a histogram. The number of locations which has two in them is approximately the intersection of the two sets, and the number of locations which have a non-zero value is approximately the union. Now, we cannot do this directly for a flipped Bloom filter because of the noise. So we use a previous work that takes the histogram. So basically, we sum the two flipped Bloom filters, we generate as a histogram, but then use a previous work to estimate what would the histogram be for the original unflipped Bloom filters. Having this, given that we can add several Bloom filters and do this, we can get any symmetric cardinality. Combining different symmetric cardinalities can allow us to also compute the cardinalities for any combination of the sets, any counting query, basically. We have applied this technique to a Wi-Fi data set provided by Cisco that has been collected in a large European city. It has 1.4 million unique devices, has been collected over 91 days. We created one blip per day, and we tried to see if we can find the temporal patterns. In the first line here, this is the number of unique devices seen each day. The ground truth is in blue, and the red is our estimate. And we can see that the temporal patterns are retained, the weekends, the holidays, and so on. In the second and third line, we compute the intersection of a rolling window of 2 days and 3 days respectively. So the intersection can also retain temporal patterns. We can also compute spatial patterns. For instance, on the same data set, we try to compute the top 10 origin-destination pairs and compare it to the ground truth using the F1 metric, and we've seen that our method, compared to a naive alternative in which we only use the histogram of the flipped Bloom filters without estimating the original values, can find that when epsilon, the differential privacy parameter, is low, hence privacy is high, our method performs significantly better than the alternative. But when epsilon is high, which the privacy is weak, there is no big difference between the two methods because the flipped Bloom filters and unflipped Bloom filters are basically the same. We also applied this on a different data set composed of HTTP request data for the FIFA World Cup website in 1998. In this case, we have computed the intersection of a rolling window of 30 days. So this is, for each point here, this is the estimate of people who have visited the site this day and continued on visiting every day for the next 30 days. So this shows that we can compute the intersection even for much more than just a few sets. Even though the difference in estimate is is not insignificant, however, the patterns are still there. One thing to note about this technique is that if a user is observed and appears in multiple blips, the more blips the user appears in, the more their privacy is at risk. However, in practice, for the Cisco dataset, 90% of users do not appear on more than 6 blips. For the other 10, they have higher risk. There's some ways to try to minimize this impact. Use, for example, to change the granularity of data collection, either on the temporal stage, so instead of days, we can make it weeks, or in space. There's also a different way which we can change the hash function used in the Bloom filters and making it secret so that different blips, even if the user is in different blips, they cannot be easily combined together. However, it's not a silver bullet, it has its own drawbacks as well. So in conclusion, we proposed a privacy-friendly technique to compute Wi-Fi analytics, which is privacy preserving. It's pan-private, so that even an attacker has full access to the system. The privacy of the users are still protected. We have shown that blips can be versatile building blocks for set operations. We provided error bounds, which are not presented in this presentation, but on the paper, which can be of independent interest for the analysis of hashing collisions for any number of sets. We provided promising experimental evaluation, not only on Wi-Fi data, but also for web analytics. One challenge that we are facing is that how to tune the parameters of our data structure to provide optimal results. For instance, the size of the Bloom filter, if it's too small, then the error is high because of higher collisions. If it's too big, the error is also high because of high noise. So the optimal value is somewhere in between, but it depends on the cardinalities of the set, which are not known in advance. For future work, we want to consider designing practical inference attacks so we can evaluate the privacy of our technique even more, allows us to be able to tune the value of epsilon, the privacy parameter. And we want to study more complex physical analytics tasks like traffic forecast, anomaly detection, and otherwise. And that's it. Thank you.
Okay. We have 3 minutes for questions. Are there any questions?
Hi, thank you for the talk. When you say that the re-identifiability increases for a user the more they interact with the system, essentially, is this when they interact, does this hold like when they interact several times with the same sensor, or like the re-identifiability only increases when they interact with a lot of different sensors?
When they appear in more than one blip. A blip is collected in a particular spatial location and also in a particular time duration. So yeah, if they appear in the several time durations or different locations, they are at risk.
Other questions? So I had a question, which was, I didn't totally understand the privacy guarantee, the differential privacy guarantee. Is a differential privacy guarantee applied every time that you're observed? So if you're observed 100 times, your privacy degrades with every additional observation 100 times?
I'm not sure I understand the question exactly.
So the differential privacy
Yes.
guarantee usually applies to a database with a user or without a user, but it sounds like it might be without a user at a specific time being a certain place, and with the user not being at that specific time or specific place.
Yes.
So if I'm seen at 100 different hotspots,
Yes.
you might eventually figure out that I'm in the data set, for example.
Yes,
Is that
absolutely.
possible?
Yes.
Okay.
Yes, this is one risk that is, yeah, that's true.
Did you tune for that possibility? At one point you'd mentioned that you were measuring intersections of, say, 30 consecutive days.
Yes.
Was that privacy guarantee then provided over 30 days?
The privacy guarantees is basically at the level of one blip. So if users appearing in 30 blips, then they are consuming much more privacy budget, they are more at risk. Yes.
Mm-hmm. Okay, thanks. Yeah, sorry, any... okay.
Yeah. Is it right that the ability to delete records from the blips increases as you can delete more records from blips, your privacy is reduced because you can't actually delete from an individual blip. You'd have to delete the entire blip. So like if I wanted to create a TTL for my data, I would have to split it by day, for example.
Yes, the total privacy budget would have to be split among the total number of blips that are produced.
Okay, that will have to be the last question. We're now out of time. Let's thank the speaker again.